I didn't know about the existence of Sackler colloquia when I was approached with this idea, but the basic premise of the meeting is, why has it been so difficult to constrain the role of aerosol-cloud relationships in climate? And I think we've got an incredible meeting as a result of that very pressing, probably order one question in climate modeling and climate prediction. So I'm going to introduce Ken Carslaw in a second, who's our keynote speaker. So what we'll do is we'll take a few questions after Ken's talk, but in general, for the speakers, we'll take one or two pressing questions of clarification relating to the talks. And then, as you see from the program, at the end of a group of speakers, we'll have the speakers come up front for more of we call it a panel discussion or more of an open discussion. And the idea is to really be provocative, and hopefully we'll come out of this meeting with some ideas in terms of where we must go to better constrain the role of aerosol-cloud relationships in climate. So with that, let me introduce Ken as our first keynote speaker.
Morning, everyone. And thanks, first of all, to the organizing committee for inviting me to give the opening talk, I think, and for setting such a good question. I think it's long overdue that we actually focus on this question. Why has it been difficult, and how would we go about it? Because I'm not sure as a community we really do tackle it in an optimum way. We tackle lots of things in an optimum ways, but I'm not sure we tackle this particular question in an optimum way as a community. So that's really the underlying theme of my talk is, how do we tackle uncertainty? What do we mean by uncertainty? And when we think about it more deeply, what are the implications for how we might reduce it? So my talk is based around global models and appreciating that a lot of what's going to come after me is talking in detail about much more detailed, more realistic cloud processing models, etc. So we know that global models miss a lot of the processes, but some of the things I'm going to say about uncertainty work across all modeling types. So I want to try and stimulate some discussion, some thoughts about what we really mean about uncertainty and how we would go about reducing it. So I want to thank my group, in particular my two statisticians, Lindsay Lee and Jill Johnson, who have been an inspiring part of my group for the last 2 to 4 years, helping us to understand uncertainty in the global models. And that's been a really sort of stimulating road to take for my group. So I thought I'd start by just reflecting on what we're doing as a community in trying to tackle aerosol effects on climate and aerosol cloud effects more specifically. If you look at the effort that we have put in to understanding aerosols, it's quite startling. Those arrows there mark the various assessment reports for IPCC starting in 1996. The first one where aerosols were estimated, their effects on clouds. And whatever you look at, there's obviously a very rapid increase in effort. So on the top left there, that's the one with the least increase. That's the European database of aerosol measurements in ground stations, which has now become this ACTRIS network. The big sharp change in the 70s was acidification, and then I guess the rise after that was aerosol climate effects. On the right is the number of aerosol campaigns, and that's probably not complete. That's just the number we've pulled together in our own database, but we've probably been fairly comprehensive. Bottom left is the number of publications on aerosol climate and uncertainty. And that's risen by a factor of 8 over the IPCC period. So we have a huge investment of effort, and yet when we look at the effect that has had on the uncertainty reduction in the aerosol cloud component of the global mean forcing, within uncertainty, if I'm allowed to say that, there is really no change in the uncertainty. Okay, the uncertainty has really hardly budged at all since 1996. So we can't possibly claim that over that period, with all of that effort, our understanding has not improved. So clearly our understanding has improved. Clearly our models have become more skillful. The models are doing more things than they ever did before. We have more confidence in some aspects of those models. And yet, when it comes to the bottom line number that we quite often write into our proposals in the first sentence in order to reduce the uncertainty in the aerosol effects on climate, we have not translated that effort into a reduction in the uncertainty in that number. Hence why we're having this meeting. So it's very timely to think about why that uncertainty has not come down. So I think that I think our knowledge uncertainty has decreased, but our model uncertainty has not. And those are clearly two different things. Our knowledge of aerosols is clearly hugely different compared to what it was in '96, but we have not translated that into reduction in model uncertainty. So that, for me, is the question. Why have we not done that? I'll go through my ideas about why that is the case. They may not hit the mark entirely. There'll be other views in the next 2 days, and I'm really interested to hear what people think is the answer to that question. So why has uncertainty not fallen? I think there's two possibilities, and probably a combination of both. The first one is that we have sufficient scientific knowledge over those intervening more than a decade, but we have not translated it into an uncertainty reduction. Okay? In which case we have insufficient methodologies. We don't apply our knowledge in the most appropriate way in order to reduce uncertainty. We apply our knowledge in some very creative ways to understand lots and lots of things, but we haven't translated that into the end point, which, let's face it, the final spread that we see in the IPCC may not be representative of what we really know, because it ends up being these big CMIP models which miss a lot of the processes that everyone in this audience has spent their lives tackling. So we probably don't have a good methodology for translating knowledge into less uncertain global models. Or we have insufficient scientific knowledge. We simply don't know some things. We don't know how clouds respond to aerosols in all the environments that we need to know it. I don't believe that's the case. I think we do have that knowledge, except that knowledge is not translated into what the models do. Okay, so I think there's, and the rest of my talk is really about that bit in blue, that we don't have a methodology for understanding uncertainty and translating knowledge into a reduced uncertainty. And others, I'm sure, will come after me and say there are many areas of our knowledge that are big gaps and we need to fill them in order to make the models better. And we've been doing that for 20 years and we've not translated it into global models. So I think it is about time we spent more time focusing on the big question, which is what is the uncertainty and how do we quantify it with the knowledge that we have, even without any new knowledge. So what is our uncertainty reduction methodology? Or do we even have one? When we do modeling and we compare our models with measurements, do we think about reducing uncertainty? I don't think we really do as a community. We say we do. We write proposals and we write papers that say we're doing something because we want to reduce the uncertainty. I don't think we actually end up getting to the point of doing that. So we start with our model, and the model produces lots of what I call state variables, aerosol optical depth, cloud condensation, nuclei, etc. And when we compare that with the same measured state variables, and of course one problem is of course that the models are not producing exactly the same thing that we're measuring, so there's that offset already, which may be in large part one of the problems, that we're not modeling what's actually being observed, or we can't match our measurements exactly to our models, so the uncertainty can't be reduced very effectively. But then we come up with some measure of model skill. Usually it's normalized mean bias or correlation coefficient or something like that. And we go through this process of adding more and more complex processes. My group does it. We come up with new nucleation mechanisms. We come up with a new line, the red one here, which looks a little better compared with the measurements. We put that new, more complex process into our model. We say the model is closer to the measurements than it was, therefore somehow, miraculously, the uncertainty has gone down, because we have a better model that's closer to the measurements. And we go through this cycle of improving our models. And that cycle clearly doesn't have a spin-off of reduced uncertainty. It has a spin-off of a more complex model. Okay, so I think there's something that we're not doing there. And then we have a CMIP where we bring in yet more models, all of which are not doing things very adequately, and we go through that cycle. And we end up with many models that we don't understand very well. So as a community, we're not very good at targeting our efforts towards reducing the uncertainty. I think we're good at targeting our efforts towards improving model complexity and realism, and they're not the same thing. So I think it's worth bearing in mind that a model that's closer to observations is not necessarily a model with lower uncertainty. Okay? If you haven't calculated the uncertainty, if you haven't accounted for all of the uncertain processes that are in your model, then just because it's closer to measurements doesn't make it less uncertain. And that's clearly the case because models hope to get closer and closer to measurements, and yet when we put multiple models together, they diverge. So this seems not to be the case. And this was nicely said in a paper here by Reto-Knutti and Sedlacek here on robustness and uncertainties in the CMIP5 models, arguing that as model complexity goes up, their robustness doesn't necessarily improve. Robustness is about useful information despite having uncertainty. And I would say for aerosol-cloud forcing, our models are not robust. We're not getting useful information from them because the uncertainty is too high. We're getting some useful information from them, but for the point of this meeting, reducing that error bar, if you like, we're clearly not getting more useful information. So I would say you can't talk about reducing uncertainty until you've calculated it. So I think we need to put more effort into calculating the uncertainty and representing it and understanding it better, rather than just going around this cycle of improving processes and not getting the rewards in terms of reduced uncertainty. So what would be the optimum? What should we do if, in an ideal world, if we had infinite resources? What I think we would do is we would pull together all our knowledge of all the possible types of models that we think are realistic. And there are many, many, many different types of models, some of them including different types of what I call a structure, different ways of representing the physics in the model. Others might be the fact that there are parametric uncertainties. Some of the parameters we don't know very well. We don't know the nucleation rate. We don't know the dry deposition rate. We don't know the process of activation very well, or the way that organics behave as cloud condensation nuclei. There are all kinds of uncertainties in there, even if we have the processes in. So there's structures and there's unknown quantities in our model, or poorly defined quantities. If we could somehow gather all of that together and push it through our observations and say, well, some of these models we thought were realistic, actually they're implausible. When we compare them to the measurements are way outside the measurements, and therefore these are not plausible representations of the atmosphere. And we would get out a set of models that we think are plausible. So that would encapsulate our complete understanding of uncertainty, all the possible different structures, all the possible different settings of the different parameters that we all agree are fairly uncertain. And then we would have a range of plausible models which would give us plausible parameter sets and then plausible predictions. Because the important thing, and I missed it on my previous slide, is the forcing is not measurable. You can't go out and measure pre-industrial to present day forcing. The way you get at it is to constrain your model by the measurements, and that is essentially constraining the numbers that are in your model, and then we rely on that model to make a prediction for us. That's the forcing is a prediction, or a retrodiction, if you like. It's going backwards. So if we took all of our knowledge and all the range of uncertainties and compared it to what we see in the real world and threw away models that didn't match that real world, that would be, for me, a measure of the uncertainty that we have. And so we're a long, long way from being able to do that. We maybe get some sort of PDF of forcing from all of these models and then a reduced PDF once we've thrown away the implausible models. So that's neglecting the fact, of course, there are unknown unknowns in here, are things we don't know about the aerosol-cloud system yet, but I'm just talking about from our current state of knowledge. We could, in principle, calculate some measure of uncertainty by pulling together all of those different sources of uncertainty and generating models to represent it. And then we would have an uncertainty reduction methodology. When we made new measurements, we'd be able to maybe throw away some additional model parts of our model space and say they're no longer comparable to measurements, and therefore we have a narrower range of uncertainty. But this is clearly a huge problem, an enormous problem, and we're not going to be able to do this. And we also know that there are going to be many, many different combinations, weird combinations of models in there that are going to give us plausible models. But I think that's the reality. That encapsulates our uncertainty. There's no shortcut here. If we think something's uncertain, then it's uncertain. We can't just ignore it and focus on our favorite thing. We have to put them all together in the same big set of models and compare. So that's the magnitude of the task. And I'm going to show you that I think we can make progress with this sort of step, going from many, many models to fewer models and narrow that uncertainty. We've not tackled the entire problem, but I think in principle it could be tackled in that way. But when you try it, it does reveal the magnitude of the tasks, and that's why I put that into my title. So that's my definition of uncertainty, if we need one for the meeting, and there are probably others. It's a range of predictions of a model accounting for all the possible uncertain model quantities, which are parameters, and the structures, after rejecting models that are implausible compared to measurements. Because forcing is not a measurable quantity, we rely on constraining our model behavior and the model state against the measurements, throwing away the ones which are implausible, leaving us with plausible models. And it must be benchmarked against measurements, okay? Because forcing is not directly measurable, at least not from pre-industrial to present day, and probably not over recent decades either. So I'm going to show you some steps we've taken to try to do that, and we are by no means complete, and people will object, I think, to the simplicity of some of the things we've done, but we are trying to take the steps in that direction. So the restrictions are, we're going to take a full global model and we're going to make lots of perturbations to it and understand what range it predicts, and then I'm going to try and reduce that uncertainty by comparing it to measurements. I'm going to throw away the implausible models and see what's left and see how much we could in principle reduce the uncertainty. So it's restricted here because we're using a nudged model, so we're not allowing for these fast feedbacks. It's a chemical transport model at this stage. We're now doing this in a full climate model. What I'm going to show you here was in a form where we don't get those fast adjustments. We're not getting all of the feedbacks on the cloud processes. We're only perturbing uncertain parameter values. We're not perturbing processes. We're not bringing in one process representation in exchange for another, which is another approach. And we're only looking at the aerosol processes and emissions. We're not looking at the cloud processes yet. In our climate simulations, those are also now included. But we have spanned 28 parameters, and in another one over 30, representing the microphysics, the removal rates, and the emissions. And I think this will be enough to give you a flavor for what might be possible if we built this system even bigger. And it certainly tells me a little bit about the magnitude of the task. It gives me some indication why the forcing may have been difficult to reduce, even if we hadn't thought of it in that way before. So lots of you have seen this slide before. I show it many times in talks like this. How we can span the full parameter space of our model. Remember, I'm just adjusting parameters in the model. They're just numbers. So you might have one parameter here. It could be a dry deposition rate, and this could be the nucleation rate or whatever. And then in a particular grid box, you've got some surface that describes how your model behaves when you vary those two parameters. And normally, of course, we just walk up one axis at a time, which in my group we call one-at-a-time tests. Okay, but really there's a whole response surface here that we really ought to map out. And then we need to extend that to all the dimensions of the uncertainties, not just one or two, which is what most modeling activity is about, just perturbing a few parameters at once. So the way you do that, you run simulations at a few points in that parameter space and then use emulators to connect those dots, essentially, and produce that response surface for you. This is a fairly complicated process, which I've had two statisticians in my group help to generate these response surfaces for the global model in every single grid box. There's software out there to do this, but the devil is in the detail as ever. So this sort of technique has been around for quite a long time, and it's just not been applied to our field. So what could we do if we sampled all the uncertainties in our model, or the ones we've chosen at least, and then get a full PDF of our model output, and then try to constrain that with the measurements? Would that work in principle? That's what I'm going to show you. So if you can visualize that in 3 dimensions, you have 3 parameters. We choose dots from a sort of a Latin hypercube sampling. They look something like that. That is pretty realistic what we're doing. And once you've got that response surface, you can then sample much, much more densely with Monte Carlo, because the emulator's fast, and therefore we can learn about every single conceivable corner of our uncertain parameter space. And to do that, for the global model that we use, we needed about 6 runs per parameter. So it was 168 global runs. Not very much, really, to map out all that uncertainty space. If we had a free-running model in which we had feedbacks and adjustments, etc., there would be noise in there. There's a whole bunch of new processes and complexities which we would have to face if we do this in a free-running climate model. But there's technology out there to help you deal with these sorts of things. So this is what we get out when we do that. And I haven't told you what the parameters are, but they relate to the aerosol microphysics, the deposition, the removal rates, the emissions, etc. And we defined the range of those parameters that we put into that sampling from an expert elicitation. And then we sample from the emulator rather than the model. So we're essentially running the model 140,000 times in Monte Carlo sampling in a fraction of the time. If we did that for real, it would take 190 years of this global model. So we're getting a lot of information on the cheap. And we know the emulator's good because we sample it again in spaces that weren't run initially and compare it. And we can come up with some measure of how good the emulator is. And the uncertainty is smaller than the aerosol uncertainty, which is what you need. So what you get out then is this PDF. And this is not a variability. Normally when we look at a PDF, we think of variability. This is actually the uncertainty in the mean CCN state. So you can see here, whereas that barrow, it goes somewhere from about 50 up to about 1,000. So a really wide range. And somewhere in here is observational reality. So what happens if we throw out things that are outside observational reality and just keep the model runs or the parts of parameter space that are plausible compared to the measurements? Okay, that would be a way to reduce uncertainty. So I've done what I said I'd do. I've calculated the uncertainty, and now I'm going to reduce it by throwing away parts of parameter space that don't work. So let's see how that pans out. So we can also calculate a forcing uncertainty, which is what this meeting's all about. We can pick that apart with variance decomposition to see what contributes to the uncertainty. I'm not going to focus on that. I want to focus on how we reduce this. We can come up with a mean albedo forcing. This is just albedo forcing, so they say there's no fast adjustments. And we can come up with a standard deviation representative of that PDF. So now I'm going to see what happens if I can chop away parts of that parameter space and see what's left and see how much we can reduce the uncertainty in forcing. So of course, forcing is not observable. I can't tell you that that value of forcing is implausible. We can't measure forcing. What I can tell you is the CCN and the other aerosol properties that went into that forcing are implausible. So we have to make state variable measurements which then inform the plausible parameter space of our model, which then tells us what the plausible forcing is. Okay, so we can't just chop at this forcing PDF because it's not something we can simply go out and observe. And I think that point is sometimes missed. We sort of think it's some kind of observational constraint on forcing. We can't simply measure it. Maybe someone will say we can in this meeting. Okay, so chopping away at the parameter space. So you can see here, here's a real case. It's just one place in our model. You can see the measurements, their uncertainty or their variability. And then you can see our ensemble here. That's just the runs, not the emulator. And you can see there's parts of our parameter space that are implausible. You can chop those out. And when we chop those away, we'll be left with a narrower range of parameters. Different combinations will be deemed to be implausible. So if you can chop away the parameter space, we get left with something, a part of parameter space. So it's important to realize when you compare with your model with your measurements, you're not defining the values of your parameters, you're defining the ranges of the parameters, okay? Because it's a space. It's 28-dimensional space. So when you make a measurement, you very rarely define a parameter, you define a range of parameters. And that is one of the problems I'm going to draw attention to now. That space that gets left might look quite different for forcing. So let's see what that looks like. And this is quite illustrative. So I'm going to show you here. This is how much the variance goes down. Because you see the initial PDF that I showed you. That's what I assume to have initial variance of 1 in every one of those grid boxes. And then when I make a measurement, and I'm going to draw that measurement from our model rather than real measurements, because I know we'll definitely find it then, plus or minus 30% on that CCN measurement, and I'm going to see how much the uncertainty goes down when I chop away at the uncertainty as a result of that. And some points down here, you can see in the Southern Ocean where we've made those measurements in inverted commas. And that's after one measurement. So one of these points in the Southern Ocean reduces the parameter space, so the variance of the constrained model is slightly less than the prior model. But you can see the forcing hasn't really responded to that measurement at all. So there's no other uncertainties in here. It's only the aerosol parameters. So the forcing is not some other sources of uncertainty in the forcing which we're not accounting for. Well, there are, but they're not factored into this calculation. So every part of parameter space we chop away because of the CCN measurement is acting on the forcing. There are no other hidden sources in this calculation. If I make two measurements somewhere else in the Southern Ocean, you can see now the uncertainty of the CCN has gone right down. We've really constrained that PDF by making a CCN measurement, which is not surprising. That's what you expect. As we step through, you can see after about 6 measurements, the uncertainty in other parts of the ocean has also gone down because the processes are the same there as in the Southern Ocean. But obviously not exactly the same because the uncertainty hasn't gone down as much as it did in the Southern Ocean. So you can see we can reduce model uncertainty by coming up with a big PDF and then shrinking it back down again. So that, to me, is what's meant by uncertainty reduction. So if you plot that one against the other, it's quite illustrative to see what's happening. And it's a bit shocking when you think about what we're actually trying to achieve, which is a reduction in uncertainty and forcing. So this is the forcing uncertainty and how much that's reduced. And this is the CCN uncertainty and how much that's reduced. So down here is no reduction in uncertainty at all. And at 1, 1, that's everything is reduced to maximum possible reduction in uncertainty. So by making single measurements in these different parts of the model, I won't go into why we chose those, but you can see that you're reducing the CCN uncertainty, but you're hardly touching the forcing uncertainty. And you can see that here, the PDF, the CCN PDF, we chop away large parts of that PDF, but the forcing PDF hardly changes. Okay, so making CCN measurements appears not to reduce the uncertainty in the forcing. And that puzzled us initially, why that was. Why? I mean, CCN isn't forcing just related to CCN. In our model it is. There's nothing else going on. Why is the uncertainty not coming down? Why is this so hard? We can use different sorts of measurements. Particle number instead of CCN, we use black carbon. We're now introducing more and more different types of measurements, and you can see they all seem to lie along this line. So we can continue to reduce the CCN uncertainty, but we don't touch the forcing uncertainty quite as much, only about half as much or less than the forcing uncertainty. So it seems like making more and more aerosol measurements, we're not reducing the forcing uncertainty in this model. Okay, and that might be a clue to why it's been so difficult to reduce it. You wouldn't have thought about it in this way, but I think it is an indication of why the uncertainty is not coming down very quickly. So I'll explain that in a little bit more detail. So imagine you have two parameters. That could be deposition rate and that could be emission rate. And that's a good example of two parameters that compensate each other. You can have high deposition and high emission, gives you the same CCN state as having low emissions and low deposition. Okay? So there's a part of parameter space of those two parameters where we can get a really tight constraint on CCN, but we can't tightly constrain the parameters. You can only constrain the relationship between them because they compensate. That works whether the contours run that way or that way, if you think about it for a moment. So every time you make a state variable measurement, you are not constraining a parameter value, you're constraining relationships between parameters. You might not actually be doing that, but that's what you're effectively doing. The problem, and why we're not reducing forcing, is because the forcing might have a dependence on those two parameters that looks like that. It doesn't have to be the same as CCN, it doesn't have to be the same as AOD, it doesn't have to be the same as any state variable measurement you make. The thing you're trying to predict might not vary in the same way as according to the parameters as the variables you're actually able to measure. So how much forcing have we constrained? This is a bit of an ache for the brain, but that's the range of forcing that's hardly constrained at all. We can now go between, what is that, less than 0.1. I made this up, of course, less than 0.1 to 0.8. So we hardly constrained the forcing by making a really good CCN measurement. Okay? So that's a real problem. So have I over-exaggerated this? Surely the real model doesn't look like that, quite so bad. Surely the CCN and the forcing match each other a little better. Well, no, actually not. You don't have to look too hard. There's 28 dimensions to look through here and lots of projections to map out, but it doesn't take too long to find an example that looks exactly like that. Here's DMS flux and Aiken mode width, both of which are uncertain in our model. And there's the CCN constraint that we put in, and here's the forcing. It runs the other way. So the forcing is not constrained by making those CCN measurements. And you could choose AOD as well. You could choose anything, and there will be a similar problem. So when something is not directly measurable, and you're relying on other variables to constrain it, you have to think how the complex multidimensional parameter space maps onto the thing you're trying to reduce the uncertainty in. So this is a word that most people won't have heard of, but you should all become familiar with. It's very important. Hydrologists have been talking about this for a long time, even long time before this particular paper, but that's a nice sort of rant almost about the importance of this in modeling of any kind. So in a model with many compensating uncertainties, there are many ways to achieve equally plausible agreement with the measurements, if you have a measurement uncertainty, which of course we do. And that's called equifinality, equally final or equally plausible models. And different parts of that parameter space evolve differently. Okay, one part here might evolve differently to that part here if we then change the emissions. And that's what's happening. So forcing is a result of change. It's not a state variable, it's a response. And those different parts of parameter space, when you map them back to the pre-industrial, they behave differently. And then the predictions diverge. And that's essentially what's happening. So a well-constrained model state doesn't imply a well-constrained forcing, because the forcing is something that's a result of a change. Okay, so we could end up with a situation where we have really good constraint on present-day aerosol, but then we try and calculate forcings or predictions, they just diverge again, because we've narrowed it down to a complicated part of parameter space that's plausible, and they all behave differently. And that's what's happening. That's why we're only able to reduce the forcing uncertainty a little bit when we make these very precise CCN measurements. So what does that mean for multi-model ensembles? Now your brain really does begin to struggle to think what this, how this maps on. But I think it does map on very well. And I don't think we think deeply enough about what we're doing when we run multiple models. For me, in a statistical point of view, a different model is just a different link between the inputs and the outputs. It might contain more complex processes that you think are better somehow, but ultimately there will be a diagram that looks like this that relates the inputs and the parameter settings to the outputs. And of course, all those different models have different structures, different parameter settings, different ways of representing the world. So all these different contours are going to be very different. And then what happens when it comes to CMIP or some other big assessment is the model group chooses a point in that multidimensional parameter space, which of course they haven't explored because it's too expensive. And they choose a point which presumably they think is plausible. They've done some comparison with measurements. But of course there are many other plausible models in there that they didn't choose. But they choose one, and then they run it for CMIP. And those different models give different forcings. And it's hardly surprising. There are many parts of parameter space they could have chosen which are equally plausible, which might have all converged on a better answer, a more consistent answer. But since we don't go through this process, we don't know about the uncertainty in these different models and the complex parameter space, and we end up just choosing one point in that parameter space, then we end up with different answers. And I think that is really the root of the problem. But even if we'd got all models to agree, let's say we got all models to simulate almost precisely the same global mean AOD today, you think that would be great. Now they'll all get the same forcings. According to equifinality, they won't, because they could have arrived at that AOD in many different ways. And then when they run backwards or forwards, they'll diverge again. Okay? So we need to think what we mean by model constraint. Just because your model agrees with measurements does not mean you have reduced the uncertainty. You've just chosen a part of parameter space that's plausible, and there are many others. And those others represent the uncertainty, okay? Not some other vague notion of how well that particular model agrees with a particular set of measurements. So before I finish, I'd just say that probably people sitting there thinking, well, this is all very well, it's a simple global model and most of the complex processes are neglected, and I agree. But we have begun to do this with cloud models as well. This is a complex microphysical model, rather simple dynamics of this sort of cloud system, and we've looked at the sensitivity of the precipitation response to aerosol, some measure of susceptibility in that cloud, and mapped out the uncertainty in that as well. So we could use that approach to constrain then the behavior of models, more complex models. It seems to work, even though that system is more interactive and more feedback's going on than our simpler global model. There's a paper in James on that. So, last slide then. What should we do? What do I think we should do? I think we should, as a community, think about how we treat uncertainty as the scientific problem to be solved. I think at the moment we are just relying on improving processes, putting them in a model, getting more complexity, and having no idea what that means for uncertainty reduction. Okay? I really don't think we know what that's doing to uncertainty, because we haven't really calculated it. So a few people who focus on the uncertainty as the problem, and then I think we have a very large number of people who work on the processes, and that's right, because the processes are complex and we don't understand them very well. But maybe if we shift the balance a bit and start working together on the joint uncertainty process point of view, we might make more progress. I don't think by working exclusively on this side that we're going to actually reduce uncertainty. Maybe people think different. I'm trying to be a bit provocative here. We need to understand how state variable measurements constrain the uncertainty. This really worries me because lots of comparisons of things like AOD and trying to get models to agree on the AOD. There must be millions of ways to get a model to produce the same AOD. Different microphysical setups, different vertical profiles, different absorption coefficient, different mixing states, etc. All give you the same AOD in principle if you explored the whole uncertainty space. And then we would run those models forward and then, oh, hang on, they all predict different forcings. Well, it's not a surprise at all because they've probably all got the same AOD for completely different reasons. So these sort of integrated measurements are going to suffer really badly from this equifinality. And I think just because we all agree on AOD doesn't mean anything, I think, for trying to calculate indirect forcing. So we need to think about that. I don't know if I anticipate some of your thoughts, but what about looking at variations? I think when we look at how cloud optical depth varies with aerosol optical depth and we get the right dependence, the right slope, the log of droplet number versus the log optical depth, etc., that must be a good measure of how well the models are performing. Again, why should one variable versus another suffer any less from equifinality than one state variable? We've just got two now. Okay, so I think when we get a good relationship between, which tells us something about the forcing, how the clouds behave in response to aerosol, we need to think, can that be explained in multiple ways as well? Could it be that models that get the same dependence also end up predicting different forcings when we go back to the pre-industrial? Once you start thinking about the unexplored parameter space, you begin to worry about what particular points we've chosen to explore. I think we need to determine how well our observing systems constrain uncertainty, not how well a particular model agrees with the measurements. They're different things. We get out of this mindset that a model that agrees with measurements is somehow a better model for predicting forcing than a model that doesn't. It could be that forcing could be predicted more accurately by a model that agrees less well with present-day measurements, okay, because of all the different points in parameter space. It's just not obvious that this should be the case. So I think we need to think more about what measurements mean for reduction in uncertainty. I'm not sure whether present-day observing systems can reduce the uncertainty until we've tested it. That's a challenge. Can present-day observing systems, cloud, aerosols, in situ, etc., when brought together, could it reduce the uncertainty? Or are they just too uncertain themselves? I don't know. I think we should challenge ourselves to do that. And then maybe the last point, we should work towards a small number of plausible models for which we understand the uncertainties and we're bothered to map them out. And this sort of ad hoc, choosing a point in parameter space and running, maybe we shouldn't use models in that way. We should put more effort into a few models to really understand what's going on and then trust those models better than the ones where we haven't bothered to put that extra effort in. Okay, I'll leave it there. Thank you.